Okay, hello. My name is Dr. Ron Darbo, and I will be having you this semester for Organic 1. I shared with you an email describing the unusual circumstances this year, and again, let me just apologize for that. But just to remind you of the way we're going to run it, it is what we call a flipped class, where I will record lectures typically on Friday afternoons and Monday afternoons. I will post them on YouTube, the YouTube channel. I'll give you the link via email on Blackboard. And then my expectation is that you will watch both lectures sometime between Monday night and Thursday morning. So the class will not meet on Tuesdays. We will meet on Thursdays at 9:30 to 10:45. That session would be largely to cover anything that you don't quite understand from the lectures, but focus principally on answering questions. It's doing a question and answer session. Let me begin a little bit by giving an introduction. I guess that's appropriate. So you would have picked up by now the mellifluous sound of my accent. I am from the Twin Island Republic of Trinidad and Tobago. It's a pair of islands in the tropical Caribbean, land of the steel band and the limbo and the calypso and so on. Really a beautiful place to grow up. Really just a wonderful place to visit too. Just a wonderful pair of islands. I did my first degree at the University of the West Indies in Trinidad. I did my master's and my PhD at Johns Hopkins University in Baltimore, and after that I spent almost 20 years at a university in Louisiana, McNeese State, and 4 years ago I moved up to Arkansas to take a position as Dean of the College of STEM. I am a physical organic chemist, which basically means we look at mechanisms of organic reactions, and we'll talk about that in great detail over the course of this lecture. I will share with you why I became a chemist, and really an organic chemist in particular. Like you, I think I've always had an interest in understanding how things work, and many people refer to chemistry as the central science. It does have a touchy-feely part to it, and you get to enjoy a lot of that in Organic 1. Some in Organic 2 as well. But it does have a small component of quantitation. And chemistry allows you to understand much of the world around you. There has been, certainly over the last 2 decades, perhaps a little bit more, a greater appreciation by the rest of the scientific community, and even outside of the community, the value that chemistry brings. Understanding the molecular logic of living things, understanding the molecular logic of climate change, of ecological disasters. A lot of it comes down to how atoms behave, and that is the purview of chemistry. And there is something wonderful, something really inherently powerful about being able to explain phenomena that are occurring around us or that are in the news. Chemistry empowers you to do that. And I say to students all the time that in many ways chemistry is an awesome subject. And I take awesome in the original intent of the word, that it's just full of awe. And if you give it the time that it needs, and it is a little bit demanding, organic, if you give it the time it needs and you come to class, you spend time going over lectures, asking questions, making sure you understand. If you seek to understand, you will have a wonderful experience in this class. It is a life-changing and a mind-opening course. I'm encouraging you to give yourself to that, to walk this journey with me and to see where it leads you. And I guarantee if you stay the course, it will lead you to places that you would not have thought your mind could go. It requires work, but I just want you to know that I'm here. I usually get in at 7:45 in the morning. I'm rarely off the campus before 6:30 in the evening. You're welcome to make appointments or to drop by and see me, and I'm happy to go over stuff with each of you individually. I would encourage you to take responsibility for your own learning, and to recognize that learning never was and never will be a passive exercise. You're required to engage with the material. He who does the work does the learning. This course will require you to work. It requires you to look at the lectures, not just as a Netflix video, but for you to engage in material. Stop the lecture, take notes, rewind if you have to, and shoot me questions by email as they arise, or in class when we meet on Thursday. Okay, so with that, I'm going to go ahead and get started on the content. I set myself an alarm to make sure we don't go over. And the first thing we talk about is what is organic chemistry. What is organic chemistry? And organic chemistry is the chemistry of the compounds of carbon, right? So it is the chemistry of the compounds of carbon, with the except for carbon dioxide and cyanide and their derivatives. So what are some of the derivatives of carbon dioxide, for example? Well, carbon monoxide, bicarbonate, and say carbonic acid. You consider these as not being organic. Okay, so carbon dioxide is the oxides of carbon, and then their conjugate acids. Those would be not considered as organic. And in cyanide, there are a couple of derivatives of cyanide that are no longer organic, that are not organic. And they include cyanate and thiocyanate. And within these, there are isomers of those, which we'll talk about later. So this is called cyanate, and this is called thiocyanate. So organic chemistry then is the chemistry of the compounds of carbon, with the exception of carbon's oxides and their derivatives, and cyanide and their derivatives. And they're really just two that are typically mentioned. Well, the immediate question then that we need to ask is, to ask and answer is, well, the periodic table has, 119, 120 elements by now. How is it that carbon, which is just one of the 120 elements, how is it that carbon gets its own branch of chemistry? So if you don't know, chemistry is typically divided into what's called A, B, I, O, P. Those are the sub-disciplines of chemistry. They are analytical chemistry, right? This is where we do quantitative work. We measure the amounts of benzene in the air, or the amounts of a particular toxin in sample. In fact, those of you, if you know someone who has heart problems, hopefully none of you do, there's a drug that is used. In fact, diabetics take it as well to protect their kidneys. There's a drug called losartan, which is on the market and has been for quite a few years, that both protects one's kidneys and also lowers blood pressure. But the makers, and I don't recall a company that makes it, there's a massive recall because losartan contains small amount, the manufacturers have indicated it contains small amounts of a chemical called N-diethylamine. And the structure of that is N-nitrosodiethylamine. The structure of that is N double bond O, and it's got a CH3, and then another CH2CH3. So this is, it's N-nitrosodiethylamine. This compound is carcinogenic, and it causes cancer. So analytical chemistry is that branch of chemistry that measures the amounts of anything. For example, the diethylamine compound in drugs. It measures, as I said, air pollution, water pollution, blood sample, and so on. Biochemistry deals with chemistry of living things. It goes through things like photosynthesis, the glycolytic pathways in humans and mammals, and so on. Inorganic chemistry is a chemistry of all the elements except for carbon. And that's important. Organic chemistry is the chemistry of all of carbon. So inorganic chemistry studies all the other elements, right? And that's a field on its own. Organic only studies carbon. And that brings up the question, why is carbon so special as to ask for and get its own subdiscipline? Okay? Physical chemistry, which if you're a chemistry major, you will take it. That deals more with the sort of mathematical underpinnings that account for chemical phenomena. So the question we're asking is why is carbon so special? Actually, while I have this on the board, let me talk about this a little bit, and we will see this in maybe late organic 1 or certainly organic 2. The reason this is carcinogenic is because when you ingest it in the stomach, there are lots of acids. The pH in the stomach is actually quite low. There's a lot of HCl that's produced in the human gut. And what happens is this reacts with H+ in the stomach and gives you this compound. So you remember from your Gen Chem that there are lone pairs of electrons on the O, and that lone pair of electrons on the O attacks H+ in the stomach and makes this species. You remember from your Gen Chem, I can draw a resonance form, and what that will do is give rise to this species. And this species is actually the carcinogen, or is responsible for carcinogenicity. It turns out that a significant cause for carcinogenesis is that the DNA undergoes a reaction where it attacks species that are electron poor. Later on, we'll see the term for that is electrified. So this carbon in the protonated version is actually susceptible to attack. So DNA, and I'm going to write DNA like this. So DNA has lone pairs, and the DNA attacks the group, and what you end up getting is alkylated DNA. So you get DNA with a CH2, CH3 group on it. And that thing, alkylated DNA, undergoes a cascade of reactions that leads to uncontrolled cell growth. The compound is particularly bad because what happens next, the The other species you get from this, and I'll draw it this way, although it's a slightly different version. The other species you get from this undergoes further reaction in the stomach. So I get another H plus coming on, and that gives rise to this species. So another H plus comes on, and H. And what happens is now this occurs. I'm going to lose water, and I generate this species. And that species looks in many ways like that one. So along comes another DNA and does exactly the same thing that happened before, and I get another one of those alkyl DNAs, and I lose nitrogen gas. So the point is, this compound is really bad because when you ingest it, so you take the pills and you swallow it, it goes into the stomach, it gets converted into the protonated version. And that actually, we say it's bidentate. It has two teeth, so it can attack two different DNA molecules or two different parts of a DNA molecule. Either way, alkylation of DNA leads to cancer. Now, this is the value, by the way, of organic chemistry, because we can understand the phenomenon. So we don't have to question, well, why does this compound cause cancer? We can, by very simple means, and we're going to go through this in the class, we can by very simple means account for the toxicity of compounds, right? We can account for the behavior of compounds. And that is a powerful thing to have. That's a powerful skill set to have, because we can explain things around us. And more to the point, even if it's not exactly this compound, if it's one that looks like it, then we're able to transfer our skill set to those things. And that really is one of the more powerful features of organic chemistry. So I'm just going to erase this because that was a bit of an aside. So the question we were asking is, why does carbon get its own branch of chemistry? What is so special about carbon? And so what we're going to do is talk about the properties of carbon that are unique, that allow it to form its own subdiscipline. So let's look at the properties of carbon. And again, these are the properties that will answer the question, why is carbon so special? And there are four of them. One, carbon is small. Now, I'm going to write them all, and then we're going to explain them. Okay? Carbon is small. Two, carbon is not electropositive. Well, I should say it has a low. Carbon has a low electropositivity and a low electronegativity. You'll remember electronegativity from your Gen Chem. Electronegativity is the ability of an atom in a covalent bond to suck electrons towards itself. So, for example, if I have H attached to Cl, Cl is more electronegative than H, and so it sucks the electrons in the HCl bond towards itself. That creates a delta minus dipole on the Cl, a delta plus dipole on the H. Electropositivity is a term you may not have heard in Gen Chem, but it is the opposite. So instead of the ability of an atom to suck electrons towards itself, as is electronegativity, electropositivity is the ability of an atom to push electrons away from itself in a covalent bond. So really, I can say here that Cl is more electronegative than H, which is why the Cl is pulling the electrons towards itself. But out of the other side of my mouth, I can say H is more electropositive than Cl, which is why the H is pushing electrons away from itself. So electronegativity is the ability of an atom in a bond, in a covalent bond, to draw electrons towards itself. Electropositivity is the ability of an atom in a covalent bond to push electrons away from itself. And we'll talk about the value of this in a second. 3, carbon is tetravalent. In other words, carbon, which of course is in group 4, has a valence of 4, and therefore can form 4 covalent bonds. And there's several ways in which you can express tetravalence, but one, so the most common one, is forming 4 bonds, and we'll look at that in more detail. And 4, carbon can catenate. And catenation is the ability of an atom to form extended chains and extended rings. Extended chains and rings. Okay, so how do these 4 properties confer upon carbon uniqueness and therefore a need for it to have its own subset of chemistry? Well, let's talk about carbon being small. Why is that important? Well, let's imagine I have 2 large atoms, 1, 2, and those atoms are bonded, right? So those 2 atoms are bonded. Here's a nucleus of one atom. Here's electrons that are being shared. Here's a nucleus of the other atom. So when I have 2 large atoms being bonded to each other, there is, by extension, a large distance between the nuclei of one atom and the electrons being shared, the nuclei of the other atom and the electrons being shared. That distance is going to be large. And in fact, if I look at this term, this distance, the internuclear distance, is what we call the bond length. So this internuclear distance, right, is what we call the bond length of the atom. So obviously, when the atoms are large, what that's going to mean is that the bond is long. Because obviously, if I have 2 small atoms, right, and they're sharing an electron pair, well then the internuclear distance is shorter. Okay, why is that important? It's important because what holds a covalent bond together is the mutual attraction of the shared electron pair for the nuclei in the bond. Okay? And the example I like to give is a true example. When I was in graduate school, I had a pair of friends, and one friend did not like the other. One of my friends did not like one of my other friends, and I'm gonna give them different names just to protect the identity of the innocent. But let's call them John and Mary. For reasons we're not going to go into, John hated Mary. Truth be told, I can understand why. Also turned out, for reasons I'm not going to go into, Mary hated John. Right? I mean, absolute hatred. And so they could never really get together because, knives would fly, blood would spill. So I had gone to Baltimore for a conference 15 years ago, and I picked up the phone and I said, "Hey John, I'm going to be in town for a couple of days. I'd love to get together with you, catch up." And he says, "Hey, that'd be great. Tell me when and where." And I said, "Absolutely." I said, "But there's a catch. I'm going to invite Mary." And so he gets really quiet on the phone and says, "Fine." So I pick up the phone and I call Mary and I said, "Mary, hey look, it's Ron, I'm going to be in town, so and so night. I'd love to get together, reconnect, talk about old times." "Sure, that'd be fantastic." I said, "One catch, inviting John." The line goes dead. I actually thought she hung up on me. Then she comes back and says, "If you feel, you must." So we got together at dinner, and when we sat, I kept looking at the knives on the table, making sure nobody was lunging for the knives. But it turns out we had a wonderful dinner, nice civil intercourse. And the reason is, see, these two nuclei are positive. If you expose two positive charges to each other, there is repulsion. Okay? But the nuclei are attracted to the electron pairs. And because this nucleus is attracted to that electron pair, and this nucleus is attracted to the electron pair serves as the glue that knits the bond together, holds the bond together. In the absence of this electron pair, right, there is only repulsion and the atoms fly apart. There is no bond. But the bond exists as long as this electron pair exists between the nuclei. So my analogy, John and Mary love me, because I'm a likable guy. John and Mary love me. And so I was the glue, I was the electron pair that held the unit together. In my absence, Mary and John would have been fighting, the police would have been called, they'd have gone to court. But because they both like me, I served as the glue that kept the bond together. But the strength of the bond, the force of interaction, depends upon the square of the distance apart. So, the larger this distance, the larger the value of R, the weaker the bond. And the bond gets weaker in a hurry because R is squared. So, large atoms form long bonds. Long bonds, large values of R, give rise to weak bonds because the force of attraction, the bond strength, is low. So again, R is the bond length, F is the force of attraction. So what this means is that small atoms like carbon, it's a second row element, small atoms like carbon form short bonds. Short bonds are strong bonds. Strong bonds persist. And what that means is that 25 degrees Celsius, that's roughly room temperature, does not provide enough thermal energy to crack the bond. And what this means then is that organic compounds tend to be stable at room temperature. Organic compounds persist. So it is important then for us to study organic compounds because they're stable under room temperature conditions. We're going to interact with them. Gasoline, fabrics, and so on, right? Foods. These are all organic compounds. So it's important for us to understand organic chemistry because we will be interacting with organic compounds because they are stable under prevailing conditions. And why are they stable? Because they have strong bonds. And why the bond strong? Because carbon is a small atom and therefore tends to form strong bonds. So the importance of carbon, one, is that it is small, so it forms short bonds are strong bonds. Strong bonds mean stable compounds that persist. Now let me just point something out here. Over the course of this lecture series, you will be asked to write descriptive answers, short essays for questions. And a question might be, explain why carbon gets its own branch of chemistry. And one of the answers will be because carbon is small. But if you simply tell me because carbon is small, that is not sufficient. And what you noticed that I just did is I talked about carbon is small. And why is that? It's a second row element in the periodic table. The smallness of carbon leads to the shortness of a carbon-carbon bond. Right? The shortness of a carbon-carbon bond. A short bond leads to a strong bond. Because if R, the bond length, is small, then F, the bond strength, is high. And if the bonds are strong, the compound is not broken at 25 degrees Celsius. 25 degrees Celsius, room temperature, does not provide enough thermal energy to break the bond. So the compound persists. And it behooves us to understand the compounds that are around us. So for example, I talked about the N-diethylamine, N-nitrosodiethylamine earlier. If N-nitrosodiethylamine was labile, was reactive at room temperature, in other words, if as soon as it was made, it began to decompose, and it decomposed in 10 seconds, well, I wouldn't worry about it then. because it doesn't interact with me. If as soon as I open the jar, if as soon as I put it at room temperature, it decomposes, well, that's not a problem. But it doesn't. It persists. It persists because it's organic. Right? And if you notice, all the atoms in that compound were small. It was carbon, nitrogen, oxygen, hydrogen. So that is a compound we're going to have to understand because we interact with it. So carbon gets its own branch in part because it's small. Okay. Carbon has a low electronegativity and a low electropositivity. So why is that important? Well, the consequence of that is that when carbon bonds to other elements, it doesn't really push electrons. So it doesn't create a delta minus here and a delta plus here. Nor does it pull electrons. It doesn't create a delta minus and delta plus here and delta minus here. So a lot of the bonds that carbon makes tend to be non-polar, or they have low polarities. So carbon-carbon bonds, carbon-hydrogen bonds, and so on, tend to have relatively low polarities. Why is that important? It's important because our environment is full of water, and water is a polar compound. Right? Water is a polar compound. And if water is a polar compound, it's going to react with polar species. And since carbon does not tend to have very polar bonds, and there are times when it does, but since carbon tends not to form very polar bonds, it is stable in contact with water. So organic compounds, as a rule, and there are exceptions, organic compounds as a rule are stable in an aqueous environment. This is important because it rains, the atmosphere has a certain amount of water vapor in it, and so if organic compounds were very polar, if carbon was very electronegative or very electropositive, it would make organic compounds very polar. Water would attack them. So you could imagine if I had an XY bond, where X was delta minus and Y was delta plus, or if I had an AB bond, where A was delta plus and B was delta minus, well then the delta minus end of water would attack the delta plus end of this bond, and I'd get chemistry. The delta plus end of water would attack the delta minus end of XY, and I would get chemistry. So these compounds would be labile, right? Labile means reactive. So for a compound, when we say a compound is labile, it means it's reactive. When we say a bond is labile, it means it's easily broken. So because carbon tends to form bonds that are not very polar, they are stable under aqueous conditions. That's important because we live under aqueous conditions, right? If not the seas, the rivers, and the oceans, certainly the air around us contains moisture. So the fact that organic compounds are stable under aqueous conditions mean we will interact with them. So when we go to the gas pump to fill gas into a car, gasoline contains a mixture of organic compounds. Well, if they broke up in the atmosphere, if they broke up in contact with water, I wouldn't have to worry about them, because as soon as I began to pump the gasoline, water would attack it and it was no longer viable. That's not the case. Those compounds persist under ordinary conditions. It is also important for us because we are an experiment in water, right? The human body, a lot of life as we know it is an aqueous phenomenon. We need water to live. And because we are made up largely of water, it's important to know that organic compounds are stable in the aqueous environment. So if we had the misfortune of ingesting organic compounds, or of getting them somehow in our bloodstream, often those organic compounds tend to persist. And so we need to understand them because we're going to be dealing with them. Okay? So organic chemistry, carbon is important because it's small. It leads to short, strong bonds, stable compounds that persist. Carbon has a low electropositivity and a low electronegativity. And what does that mean? The bonds are relatively nonpolar, therefore they're stable in an aqueous environment. We are an aqueous environment, the human body is self-contained, and we live in an aqueous environment. So because we're going to be interacting with those compounds, we need to understand them. right? And therefore we're going to create a separate branch of chemistry to deal with these compounds. Carbon is tetravalent. So carbon is in group 4 of the periodic table. So it forms 4 bonds, that's the tetravalence. The issue with that is that carbon can exhibit that tetravalence in several ways. One is that I can form 4 single bonds. Okay? Or I could form a double bond and 2 single bonds. Or I could form a triple bond and a single bond. Or I could form 2 double bonds. Now, for reasons we'll get into later, I can't form a quadruple bond. So I can form 4 single bonds. I could form a double bond and 2 single bonds. I could form 2 double bonds. And I could form a triple bond and a single bond. So carbon has several ways in which it can manifest tetravalence. Several ways in which it can form 4 bonds. Now, bear in mind, if I am nitrogen, which is trivalent, nitrogen could form 3 single bonds, a double bond, a single bond, and a triple bond. If I'm trivalent, I have 3 options. If I'm divalent, like O, I can form 2 single bonds, or I can form a double bond. If I'm monovalent, like H, I can form a single bond, and I'm done. So tetravalence, the highest valence you can have, is tetravalence. Carbon has tetravalence, and therefore has a multitude of ways in which it can undergo bonding. And what that leads to is 2 things. It leads to complexity and variation. So there are a number of ways in which, by expressing its valence in several different ways, carbon can, with the same set of elements, generate compounds that look very much different from each other. I'll give you a simple example. So suppose I ask you to draw some compounds of carbon that have 1 carbon, 1 N, so 1 carbon, 1 carbon, 1 N, and then the rest are H's. Okay? Well, I could say 1 carbon, 1 N, so I can make this compound. 1 carbon, 1 N, I can make this compound. 1 carbon, 1 N, I can make that compound. Okay, well, I couldn't do anything else with this one. I need to have some more for that, because I can put the N here, but I can't put another carbon, because I only have 1 carbon. But look, this is 3 different compounds that I can make. Right? With just that simple set. 1 carbon, 1 N, and just fill in the H's. Imagine if I had 2 carbons, or 2 carbons and 2 N's. The amount of variation and complexity starts to magnify. And one of the things that you will learn, and we'll talk about this in the next lecture, is there is a very basic precept in organic chemistry that if you follow certain basic rules called a structural formula, the only limit to the compounds that can exist is your imagination. So what you end up having with organic chemistry is just a huge complexity of organic compounds. But something else happens. Because it's tetravalent, you also end up with not just a lot of variation, but a lot of different compounds. Right? A lot of different compounds. So if I ask you to draw a compound that has 1 H and 1 N, well, then that has 1 N and H's, the only compound I can draw is this. Right? The only compound I can draw is ammonia, 1 N and H's. Right? But if I have, in the case of organic, or with carbon, I can end up with a large number of compounds and a large amount of variation. And in fact, it turns out, when we get to catenation, we'll amplify it. It turns out that the number of organic compounds that are known, if you add all the inorganic compounds that we know, sodium chloride, potassium nitrate, blah, 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 blah. If you add all the inorganic compounds that you know, and you multiply that by 1,000, it doesn't even approach the number of known organic compounds. Doesn't even approach it. So all of it's just carbon as a central element. The number of organic compounds that exist, in part because of the tetravalence of carbon, is huge. And chemists just couldn't handle all the inorganics and all the organics under the same umbrella. So the decision was made, quite rightly at the time, to separate them out. Because there are certain unique features of organic compounds that need to be addressed separately. The other feature with carbon, I'm just going to check my time to make sure I'm not over. The other feature with carbon is that carbon can catenate. And catenation is the ability of an atom to form extended chains and rings. Carbon can attach itself to other carbons and to some other elements. Let's take carbons. So that the chain could extend 10 carbons, 1,000 carbons, 1,000,000 carbons, 1,000,000,000 carbons, all in the same line. The next element that comes close is sulfur. Sulfur goes to 8. Carbon can go to 1,000,000,000, 10,000,000,000, 1,000,000,000,000. And that leads to complexity. But carbon can also form rings. So, for example, if I take, let's say these, let's say I take 5 carbons. So if I say to draw, skeletons, 1, 2, 3, 4, 5. 5 carbons, a compound with 5 carbons. I'm going to put H's on there because I don't like it looking naked. So if I have 5 carbons, okay, I can have them in an unbranched chain. I can have it in a chain that is branched. I have them in a chain that's branched. So these are 4 in a row. I'm sorry, 5 in a row, 4 in a row. I can also do it where there are 3 in a row. And by the way, putting this group here is the same as that. And putting it here and there are the same. Putting it here and here is the same as putting it there, which is making the same compound. I could have 3 in a row, right? And I can put a carbon here and a carbon here, and that's an entirely different compound. So carbon's ability to form extended chains, to form chains, creates, just in this case, a large number of compounds and certain variation. But I don't have to have my carbons all in a ring, or all in a chain. I can put them in a ring. And the ring could be 5-membered. Right? So the ring could be 5-membered. The ring could be 4-membered. Right? So I can have a 4-membered ring with a 1-carbon appendage. And you notice I'm careful in keeping the valence of the carbon and the H constant. Carbon is always a valence of 4. I could have a 3-membered ring, and I could do something like this, a 3-membered ring. And either I could have a 2-carbon appendage, right? I could have a 2-carbon appendage. Or I could have 2 1-carbon appendages. A carbon here and a carbon here. So just with 5 carbons, if you look on the board, and these only have single bonds, mind you. I didn't do any that have double bonds or any that have triple bonds, because that would even magnify the menu even more. But the point you want to get out of all of this is that the ability of carbon to form chains and rings, its ability to catenate, creates large numbers of compounds and large complexity of compounds. And so, again, as was talked about with the tetravalents, the decision was made that there are just too many organic compounds and there's too much variation to lump them all together with the elements of the rest of the periodic table, the other non-metals and the metals and so on. So, in a nutshell, these are the reasons why carbon gets its own branch of chemistry. That is a wonderful question to ask in the discussion question. What are the properties of carbon that lead to organic chemistry as a separate field? And I'd expect you to say the properties of carbon are that it's small, low electronegativity and electropositivity, tetravalent, catenation. And then explain how each of those features leads to either the stability and persistence of organic compounds, or leads to the large numbers of organic compounds and high complexity. By the way, there's an interesting feature here as well. I could ask the question, why do organic compounds form the basis of life? So all of our biological molecules, our proteins, our carbohydrates, or lipids, or nucleic acids, the whole list of them, they're all organic, they're all carbon-based. So why? Why is it that life chose carbon as a central element? Well, because carbon is small. Therefore, it leads to short bonds, strong bonds, stable compounds. Well, life is a complex phenomenon. You need the biomolecules that support it to be stable. It would not help us if when we stepped out in the sun, we melted. Right? So we want, or at room temperature, when we're sitting on chairs in a lecture room, we all just sit and melt. Right? So it's important for organic compounds to be stable. Small atom, short bonds, strong bonds, stable compounds. Okay, life looks at that. Carbon has a low electropositivity, electronegativity. What does that mean? It means its bonds are not very polar, which means they survive in an aqueous environment. Not only is the atmosphere aqueous, right, because we breathe in moisture, we are built of water. We're 70-something% of water. Do we want organic molecules to dissolve in our bloodstream? Right? No. We want organic compounds to be stable in an aqueous environment. Plus, it's nice to go swimming. Okay? So, this is important. Carbon is tetravalent. Well, what does that do? Tetravalence means I can form a large number of compounds, and the complexity and the variation is huge. Life is a complex phenomenon. We need the currency of life, the biomolecules, to also be complex. To support the complexity that is life. The array of nucleic acids, the array of vitamins, and the array of the amino acids, and so on. We need to have the complexity to support something as complex as life. The only element that supports that complexity is carbon. Same thing with the catenation. If you look at the vast majority of organic compounds, they've got rings, sometimes rings upon rings upon rings. No other element in the periodic table can do that. And so if you want to have a robust menu of compounds from which to draw for your biomolecules, well, you go after carbon. So it's not surprising then that the very features of carbon that justify it having its own sub-discipline under chemistry are the very same features why life chose carbon as the element upon which to be based. So I can ask you that question is, why is carbon central to life? Well, it's the very same question. Right? This underscores a point. Your job is to understand. Because if you understand, you can apply your understanding to any situation. There is, and I'll just say that up front, there are a fair number of things in organic that you have to remember. In many ways, organic chemistry is like a new language. And if you go to Japan and you want to survive, you got to know the words for airport, for cab, for hotel, for bank, for restaurant, for embassy. Right? You got to know those words to survive. It's the same with organic chemistry. You have to know certain vocabulary, certain concepts you must know in order to survive. But beyond the things you must know, there is a wonderful array of things you must understand. Memory will fail you from time to time. Right? In the heat of battle, the exam, you might forget stuff. But if you can reason it from first principles, because you understand it, that never abandons you. So a lot of what we will do in this course, when we discuss stuff, is I will explain it to you from first principles, right? And my exhortation to you is that you develop that skill set, because that will allow you to explain, not just to explain stuff, but to seek to understand so you can explain. Right? This is not just about learning stuff and memorizing it, because if you do that, it cheapens the material. Plus, you disconnect yourself from the potential value of the educational process. Don't cheat yourselves by trying to cram stuff, God forbid, the night before. Give this the time it needs so you can wrestle with concepts and then soak in. You will benefit from it. Okay? Okay, so we talked about what is carbon and why is carbon so special, and also tied in why carbon forms the basis of life. I would very briefly talk about a concept called vitalism. And vitalism is a very old concept. So this is really just an aside. Vitalism. Vitalism was a concept from the Middle Ages that basically held that organic compounds, and that's why the name is organic, that they could only be formed from organic matter, from living things. And that all living things, all organic compounds that were part of living things, could only be formed from that vital divine spark. So basically, organic compounds were the purview of living things because God imbued living things with a vital spark. And that gave them the ability to generate organic compounds. So organic compounds coming from living things that have the divine vital spark could only form from organic material, from living things. So the theory of vitalism held that organic compounds could only be formed from the divine, from the vital spark. There was an experiment done by Friedrich Wöhler, who took ammonium isocyanate and heated it and generated this compound. And for those of you who don't know, this compound is urea. And so if you look, this is N2H4CO. So this was just a conversion of this compound into urea, right? We didn't. It was just an isomerization. We made a new compound. But this is inorganic. Ammonium and isocyanate is a derivative of cyanide, which we said is not organic. So here we're taking something that is inorganic, we're heating it, there's nothing divine about heating, and we generate an organic compound. Urea is one of the major components of urine. We also sweat it out, right? So it's clearly organic. And our ability to make something organic, absent the vital spark, got rid of the theory of vitalism, right? And you guys, you know this. Scientists propose hypotheses that mature into theories. And theories survive only as long as verified counter data arise. So as soon as Wohler showed this experiment to the scientific community, a theory that had existed for a couple hundred years, they got rid of, because there was now proof that this was not true. So we have theory of evolution, theory of gravity, blah, 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 blah. The minute somebody proves that those things aren't true, the scientific community will abandon them for the new theory. Science is not stuck to a dogma. It is not, and it can't afford to be. Right? And this is a really good example of that. Let's talk about formulas. So there are 3 types of formulas. Now, I'm just going to make the assumption that as you watch these lectures, you will pause them as you need, rewind as you need, take a break as you need, and go on. Me, I can do this stuff all day. So, let's talk about what? Let's talk about formulas, right? And there are 3 types of formulas that we need to be aware of over the course of this lecture series. So we need to be aware of, just checking my time, 18 minutes. There are 3 types of formulas. So formulas. There is the empirical formula. There is the molecular formula. And then there is the structural formula. Let's start with the first. So the empirical formula gives the identities of the elements in a compound in the simple whole number ratio. So I'll say it again. The empirical formula identifies which elements are in a compound and identifies them in the simple whole number ratio. For example, it might be I have a species whose empirical formula is CH. Okay? Well, what do I know? I know that is a hydrocarbon, right? It's a compound having only the elements carbon and hydrogen. Those are called hydrocarbons. Now, what does that tell me? Well, I know that compound will burn, because anything having C and H, doesn't matter what else they have, they can have CH and O, CH and N, CH and lead, doesn't matter. If I've got C and H, I'm going to burn. So I know that thing is flammable. I also know it's not going to dissolve in water, right? Because water is a polar compound. C and H compounds are completely non-polar. They will not dissolve in water. So just knowing the formula tells me this is a flammable, combustible compound that is immiscible with water. And that's powerful to know. That's important to know. I know I'm not going to store it anywhere near a heat source, right? I know that it's not going to mix with water, and that's information to have, and that's good. Okay. But CH could mean the compound has a formula, maybe C2H2, it could be C6H6, it could be C100, H100. I don't know which. And that's important, because C2H2 is light. That's going to be a gas at room temperature. C6H6, that's modestly heavy. That's a liquid at room temperature. A volatile liquid. C10, this is C20, C10, H10, that is a liquid, but its boiling point is higher than that one. C100, H100, that's a solid at room temperature. Now, I know these things, and I will show you as we go through the series how you can tell that. It's not magic, it's not voodoo. So, yes, CH tells me things. It's flammable.